transition. And interestingly, all we see is a very gradual decrease of intensity as you go from the lowest temperatures up to, say, 700 millikelvin. And if we just plot the specific heat here, this is an important point, so it has to have flames. You can see that this is where you would expect a sharp change in the intensity of the peak, but we don't see that. And this is actually the same temperature dependence that we get for the diffuse scattering in the single crystal near the 111 peak. So this is an odd result. And one thing I want to point out is that it is a first order transition, and we are we were measuring this on warming. So you might think there could be some hysteresis, but this is quite a large amount of hysteresis if that's what's causing it. And so this is, I think at this point, sort of an unexplained result. So just to summarize the elastic scattering, you might think about this collinear ferromagnet, which I think most people sort of assumed was close to the ground state for terbium titanate. The terbium stanate has been shown to have a splayed XY-like ferromagnet where theta is negative 10 degrees. So that's something that's been determined by diffraction. Now, a terbium titanate, we believe, has this ice-like splaying with a 14-degree splaying angle. Furthermore, we have about 53% ordered moment, and there's no sharp onset of the elastic scattering at the phase transition. So now let's take a look at the inelastic scattering. So this is the time of flight measurement on the disk chopper spectrometer. Here is the pattern at 8 Kelvin in zero field. This is all in zero field, by the way. We never applied a magnetic field at all to this sample, as you probably would not want to do since it's a powder. And that can cause some problems. So what we have here is the zero field high temperature SQ and omega. And then as we pull down to 2 Kelvin, which is about the mean field interaction strength of the material, you see the development of some scattering here near Q equals 0. And then going further to 800 millikelvin, not a whole lot changes. Maybe you can start to see some changes building up here. 300 millikelvin, I think you can start to see a pattern. There's not really much happening. And then at 100 millikelvin, nothing happens. And this is going from 300 millikelvin to 100 millikelvin is going through this sharp first order phase transition. So taking a look at some of the energy cuts here, we've shown here the low Q integrated energy cuts. So this is in mod Q because it's powder average. So going out in Q, you start to see a change from what looks like a quasi-elastic energy dependence to something that has more of a broad plateau as you go out in Q. And again, this just serves to highlight that for all of these low temperature line shapes, there's really no change in the SFQ and omega going up to 2.5 Kelvin. You only start to see a change as you go beyond that. One thing I'd like to point out is that if you were to take the exchange parameters, for example, the ones that we determined in this paper in 2011, and calculate the zero field ground state and the spin waves from this ground state, what you would find is a splayed ice ground state like the one we found, but with a much smaller splaying angle. And you would also see this gap of about 0.2 millielectron volts to a single magnon dispersion. We clearly do not see that. I think it's instructive to look at the line shapes compared to the crystals. So this was a data set that we presented back in, I think it was 2011, on the single crystal that I showed you before that doesn't order. And we looked at the Q dependence, the energy dependence in different regions of the HHL plane. And what we see is that when you're on this diffuse rod of scattering, there's this quasi-elastic line shape here that extends out past about 1 millielectron volt. And then then if you go off the diffuse scattering into one of these more dark regions, you don't see this quasi-elastic signal. You see this kind of plateau, which is around 0.5 to 0.6 millielectron volts. And the same kind of signatures are seen in the powder. So here is the low Q integrated signal. It looks very similar to the on-rod scattering. And as I mentioned before, it doesn't change at all from going from 100 millikelvin to 300 millikelvin to 800 millikelvin. And as you go out further in Q, you see this plateau, which is around the same energy of 0.5 to 0.6. So this suggests that the line shapes are basically, for all intents and purposes, independent of the specific heat. Not only do they not change as you go through this first order phase transition, but they also don't seem to depend on whether it's a crystal or a powder, which we know have very different specific heats at low temperatures. And so that's a puzzle, I would say. Finally, I'd like to point out that ytterbium stannate is an extremely related material. The only difference is that you change the non-magnetic B site cation. And this unfortunately means you can't grow single crystals of this material because SnO2 is very volatile. But the powder samples have been investigated, for example, in this PRB from 2013. And what they found, and what other groups have found, is that there's a splayed ferromagnetic ground state similar to the one we've seen in ytterbium titanate, but with the opposite splaying angle. But importantly, the spin excitations are similar. They have this diffuse continuum-like excitation, and they look almost identical, except this has a lower bandwidth compared to ytterbium titanate. So I would argue that the same physics is at play in both of these materials. You may have seen this paper but not realized that the SQ omega was so diffuse like this, because it was presented like this with a higher temperature 20 Kelvin background subtracted. And when you do that, what you see is this almost looks like a ferromagnetic spin wave, but it's highly overdamped. So really the only difference between the low temperature, say below 2 Kelvin, SQ and omega, and some of the higher temperature data sets like 20 Kelvin, is that you see this dispersive excitation, which is strongly overdamped on top of it. And ytterbium titanate has the same sort of pattern. So in summary,